So far in 6002, you've seen how by making some simplifications of Maxwell's equations, we've ended up with very simple algebraic laws that can be used to analyze circuits. And in this little playground of ours, really good things happen. This is our EECS playground, where by making some simplifications, we've been able to really come up with very simple techniques for analyzing circuits. So today, as we build up our arsenal of techniques for analyzing circuits, we'll look at a further simplification. We will look at a part of this playground in which linear circuits reside. These kinds of circuits allow us to use some even more powerful techniques to analyze them. These new techniques that you will learn today include superposition, Thevenin, and Norton. It's pretty amazing to think of these techniques as the bazookas of EECS. Okay. Let me start with a quick review, as is my usual practice, of what we've seen so far. So the circuit analysis methods you've seen so far include, first of all, the KVL, KCL method. In this method, the KVL, KCL, and the element rules are used to analyze circuits. So the KVL method, as you've seen before, is one where you take the various voltages in a loop in a circuit, and they should all sum to 0. Similarly, the currents at any given node must also sum to 0. That's KCL. And so you apply these KVL, KCL, and element rules to circuits and then go solve them. But we did see that they ended up with a very large number of equations that were quite messy to resolve. The second technique that we looked at last week included circuit composition rules, where you applied some of these rules to compose resistors and other elements and solved circuits that way. And then we looked at the node method, where you chose a ground and in a circuit, and then you applied KCL at each of the nodes, reference to the ground node. And what was interesting was that the KVL was implicit in the pattern that you used in the node method, where the pattern was the EI minus EJ divided by the resistance of a given edge. This was a pattern that you really borrowed from KVL, and this was implicitly used in the node method. The node method, of course, is the workhorse of 6002 and can be applied to all kinds of circuits. It really applies in this entire playground of ours. So when in doubt, simply go ahead and apply the node method. Okay, as I promised, we'll now look at the smaller region of the playground and see if some interesting things happen in that playground. So to give you a quick review, I will start by looking at some basic properties of linear circuits. Following that, I will look at the superposition toolkit for your arsenal of techniques to analyze circuits. And then I will talk about the Thevenin method. And finally, I'll talk about the Norton method. Okay, so let's get started with linear circuits and see what linearity means. So I'm going to do an example using the following little circuit, in which I have a voltage source and a current source, and my goal here is to find the voltage at this node E, and I'm going to pick a ground node here and find the voltage E reference to this ground node that I've just marked out for you. So to analyze the circuit, you first write down the node equations, and I'll write down the node equations for the node. That's the only node for which we have an unknown. Recall that I have another node here, but because that is connected by a voltage source to ground, its voltage is simply V. Okay, let's start by writing the node equations for the node with unknown voltage E. So let's start by looking at the current that goes from the node with voltage E to the left, and so I take E minus V divided by R1. That is the current headed in the direction from E to V, and then I add the current that is going down this edge, which is simply E divided by R2, and then I take the current that is headed in this direction, and that is simply minus I. According to the KCL rule, they all sum up to 0. So the first thing you will notice as you write the node equation right away is that this equation here shows you that it is linear in the various voltages and currents E, V, and I. In other words, you don't have no terms that are EV or V squared or VI and so on. So this circuit here is characterized by the node equation, and notice that it is linear in the EV and I terms. Okay, let's go ahead and look at this in some more detail, and I'm going to simplify the equation a little bit more to really get a much clearer sense of the linearity here. So I've written down the node equation, and I'm going to simplify it by rearranging some of the terms in the equation. So let me collect the various coefficients. So let me write down E on this side and look at and collect all the terms that multiply E. So I see a 1 by R1 term here. Let me write that down. I see a 1 by R2 term, and so E is my unknown. Let me collect the knowns on the right-hand side. So one of the knowns is I, so let me move it to the right-hand side and put that there. The other known is this one here, V divided by R1, and when I take it to the right-hand side, it becomes plus V divided by R1. So let me introduce a little bit of nomenclature here. So notice I've rearranged the terms, and I get some coefficients multiplying E, and that is the sum of the sources V and I, where V has been scaled by 1 divided by R1. So when you look at these terms, let's understand a couple of things. Let's understand a couple of things right away. So if you look at the coefficient of the unknown E, in general, when you have a much larger circuit, it is not a single value, but rather it is a matrix of values, and it's just good to know these terms. It's called the conductance matrix. Similarly, it's usually given the symbol G. Similarly, the node voltages becomes a column vector of node voltages, and it's given the label E. And then on the right-hand side, you have the linear sum of sources, and that is given the term S. And so you get the form G times E equals S, where G is a matrix, usually. E is a column vector, and similarly, the sum of sources ends up being a column vector as well. So with that bit of cultural background in terms of what these things are called in general, let me simplify them further. And what I get now is let's try to have E on the left-hand side all by itself and divide both sides by the coefficient of E. And this guy here, if I simplify it, becomes R1, R2 divided by R2 plus R1. So when I multiply out both sides by that, what I end up getting is I have V here and I have the I here. So what is the coefficient of V? So I multiply both sides by R1, R2, and so R1 and R1 cancel out. So I end up with R2 at the top, and I get R1 plus R2 down here. Similarly, so what do you think we get for I here? For I end up with R1, R2 divided by R1 plus R2 down here. So notice that the linearity becomes much more obvious at this point, where my unknown E is some constant coefficient times the voltage V, and some constant coefficient times the current I. In other words, E is of the following form. E is some constant coefficient times my first source, some constant coefficient times V2, and so on, plus some other coefficient times I1, some other coefficient times I2, and so on. So if you look at this form here, notice that this is linear in the sources VI's and II's.